Okay, so in the last class we have looked into the JK flip-flop, and we also saw that there is this condition called the racing condition that is going to exist in a JK flip-flop, which looks like this. But we call it a JK flip-flop, but it is actually a latch configuration, because as you can see, this is a level triggered circuit, right? There is no mechanism here to do edge triggering the way we have done it in case of a D flip-flop, right? So in case of a D latch, if you remember, a latch was a level triggered circuit, and when we appended to D latches and put a clock and a negative clock to the successive two D latches, we could make a D flip-flop. That was an edge triggered circuit, right? Here this is a level triggered circuit, and we could see that if J equal to 1 and K equal to 1, the output Q is going to toggle, which basically means that if it was a 0, it is going to become 1, and if it was originally 1, this is going to become 0, right? And the problem was that that as long as the clock is going to remain high, even if it toggles, right? If Q becomes, if it was 0, it has become 1, if it was 1, it has become 0. The next time, as you can see, there is a feedback which is coming back to the respective front layer of the circuit, the front NAND gates. This is going to change the values, right? So as long as the clock is 1, the feedback from Q and Q bar are going to be fed back to the front layer of the NAND gates, and that is going to keep the system toggling in an uncontrolled way, right? That was known as racing, and the only way to make the racing not happen, or not really have uncontrolled number of times, was to make sure that the timing pulse or the clock that is going to be one for a period of time, that has to be very, very short, right? And in that way it could make sure that before the Q feedback comes back to the front part, the clock is set to 0, right? So in that case it is just going to toggle only once, but it is an impractical proposition. It's kind of very difficult to make the latch, make the clock pulse so narrow, right? Because itself the NAND gates are very, very fast, so this is going to come up as a feedback anyway, right? And this is not a very good solution. So the solution to kind of remove this racing condition in between these NAND gates is not really having the clock pulse really narrow, because that might not work in a practical case. The solution to that was very similar to what we have done in case of a D flip-flop. Okay, so what did we do in case of a D flip-flop? We took D latches, two of them, and connected them to the clock, and the other one was connected to a inverted clock, right? And in that way we could make sure that the circuit becomes edge triggered. So here also we do the same thing. I think we have discussed this, that there is a first part of the circuit is called the master latch, and this is controlled by the J and K inputs. And the second part, so if I draw a line, the left hand side is the first part of the latch, which is basically denoted as the master latch, and the second part, as you can see, we are providing clock bar, okay, instead of clock. This is clock bar, very similar to the D flip-flop, where we are actually supplying a clock bar to the second part of the latch, right, second latch. Okay, and note that the feedback does not come from the master latch to the front. The feedback actually comes from the slave latch. Okay, so this is the one which actually goes as a feedback. So if you can see, there are these two latches. This is a basic SR latch sort of a combination, right? And there are these two feedbacks and all. It basically acts as an SR latch. Similarly, the slave latch acts as an SR latch, and these are the two controls for the JK. just that this SR latch is not fed back. Okay, so if there is any racing or anything that may happen, right, so this is going to happen here, but there is no feedback, so nothing like that is going to happen. And once the value sort of comes to be whatever value it is, right, it does not depend on the pulse width, right. We are not going to look at how long the clock is high, because here it is the clock bar, and clock bar simultaneously applied basically means filters out the edge part of the clock. Okay, and so this is going to make sure that whenever there is a clock edge and j is equal to 1 and k is equal to 1, q is going to toggle only once. Okay, after that it will stop till the time it faces the next clock edge. If there is another clock edge, it will toggle another time. Okay, but that's the assumption. So kind of the edge locks the toggle, whereas in case of level triggered, as long as the level is high, the clock is the Q's value is going to continuously toggle. Okay, so this is about the master slave JK flip flop configuration, which is going to solve the race condition issue. So if remember, if j is equal to 1 and k is equal to 1, q should be equal to q next rather is going to be the q presents bar. Okay, this is another way to view the circuit. There is a first JK flip flop, as I told you, is behaves more like a latch, and second one, and you have a q and q bar going back as to the j and k inputs. Okay, and this is how this thing our master slave JK configuration flip flop is going to look like. Okay, so this is about it. We have studied this several kind of latches. For example, we started with the SR latch, followed it up with a gated SR latch. There was a forbidden state, right? And so we have used this D latch with a write enable. So we could use D and D bar are going to be fed to the different the top gate and the bottom gate, right? And this removes the problem of this forbidden state that RS flip-flops or the RS latches used to have. And then we saw that D latches was level triggered, we made it edge triggered by introducing one more flip-flop, and then we looked at the JK flip-flop, which is basically having one more extra feedback, right? So we will introduce one more kind of a flip-flop later, that is known as a toggle flip-flop or T flip-flop. And in T flip-flop, this is just the same as the JK flip-flop, but just that J and the K inputs are tied together. So we are going to look into a detailed analysis of this T flip-flop later. Just for now, you can think of this as a JK flip-flop, right, where GA and K inputs are the same. Okay, and we call it T. Okay, so this is called a T flip-flop. You can yourself understand how it behaves, because if T is equal to 1, J is going to be equal to 1 and K is going to be equal to 1. So that means it's going to toggle the value of Q. Whereas if T is equal to 0, J should be equal to 0 and K should be equal to 0. So this is more like a memory hold state. So Q is going to retain its value. This is very similar to how we modified SR flip-flop into a D flip-flop. In case of SR also, if you remember, we just had a input for D. Of course, there was a gate control and there was a D not, right? Making sure that I always give you D and D bar. So kind of similar concept, but this is called a T flip-flop. Okay, so let me come back to those details later. First, since we have understood these few flip-flops, let us try to see that how can you design circuits using, let's say, this JK flip-flop. Okay, so but before that, we want to introduce a new concept called excitation tables. So if you remember, in case of combinational circuits had a or has a input to output mapping. So what does a combinational circuit tell you? A combinational circuit tells you that what is the output as a function of the current inputs. Okay, so that is called a truth table for a combinational circuit. Okay, so in case of our flip-flops, here also you can find out that if the inputs are here, let's say for a JK flip-flop, if input is equal to the inputs are J and K, and and this is a flip-flop, that is an edge triggered circuit, there is a clock, what should be the output? Okay, given that the current output, because there is going to always hold a state, right, there could be an initial state of the flip-flop that we are considering, that is going to be called Q0. So as you can see, if I put J equal to 0 and K equal to 0, and this is edge triggering that is happening, Q is going to remain Q0. So this Q is typically referred to as Q plus or Q next. What is going to happen next? Okay, that is going to be Q0, because the contents are not going to be changed. Typically this is also called the memory hold state. Okay, so J equal to 0, K equal to 0 is the memory hold state. It's not going to change the contents of the current contents of the flip-flop. If you put J equal to 0 and K equal to 1, Q, the value of Q is going to be reset to 0. Okay, so if you put Q equal to J equal to 0 and K equal to 1, irrespective of the value of whether Q0 was 0 or Q0 was 1, doesn't matter, it is going to be overwritten by the value 0. Okay, the vice versa, right? So J equal to 1 and K equal to 0 is going to set the value of Q. Okay, and Q bar are complements of each other, that we already know. And last one is the famous case. We have already discussed this in the state table diagram, if you remember earlier. So it is just in a tabular format. J equal to 1, K equal to 1, Q next is going to be Q0 bar. So currently my output is Q0. If I put J equal to 1, K equal to 1, next state is going to be the complement of Q0. That is why it is known as Q0 bar. So this is all about the truth table. Okay. So the other kind of thing that we should ideally look at in case of sequential circuits is called the excitation table, because there we are concerned not only about the current state, but we want to design the next state, or we want to predict the next state, right, as a function of the inputs J and K. Okay, so if my present state is something, what should be, and say I want a next state, right? If I am going to be at 0, I want to go to 1, right? What should be the possible input combinations for J and K? That is called the excitation table. Okay, so let us see here. You have the outputs, right? And the output Q has two things. One is called the present state, which is typically referred to as Q, and then there is a next state which is referred to as Q plus or Qt plus 1 or whatever. Okay, so that is the future state or the next state. Okay, and the input to the circuit is the J and K flip-flops. Okay, and depending on how many flip-flops you have, you might have multiple flip-flops to make a sequential circuit. We will take a look at those designs very soon. You might have multiple J's and K's inputs. If you have only one flip-flop, of course excitation table is going to represent the characteristics of a single flip-flop. In that case, we are just going to have one J and one K. Okay, so now let us look into the different possibilities of the excitation table or the state transition, because the present state going to the next state is called a transition. Okay, and what is being transited? The state is going to be transited from a current state to the next state. So there are four possibilities, right? 0 can go to 0, 0 can go to 1, 1 can go to 0, 1 can remain 1. Okay, based on that, we might have to design circuits at a later point of time, and we need to know, to achieve this kind of a transition, what should be the inputs. Okay, so if we see 0 to 0, you can ask yourself that what should create, you can look at the state table, the truth table on the left hand side, and see that what should be the value of j and k, right? So if you see 0 to 0 could mean I am retaining the memory. It's a memory hold state, right? The content of Q doesn't change. So what should be the value of Jk? The value of Jk could have been 0, 0. But now you can also argue that I don't care what the present state is. The next state is anyway 0, which basically means that I want resetting the circuit. Okay. So if I want to reset the circuit, J is equal to 0 and K equal to 1. And that is the reason we have no dependency on K, but the dependency is only on J. So J is equal to 0, whereas K is equal to 0 is also fine, 1 is also fine, which basically means that K becomes don't care. Okay. So 0 to 0 is going to be 0x. Similarly, we can also look at one case, 0 to 1 case. You can say that 0 to 1 means I am setting the circuit. Q is equal to 0. I don't want to know whether it is 0 or 1, but what I care about is that the next state is going to be 1, right? So what can I do to a circuit such that Q becomes 1? I can set the circuit, which basically means that J equal to 1, K equal to 0. You might say that no, I want to look at from a different perspective. I want to say it was 0, so it became 1. So this is toggled. Okay. So you can also say that J equal to 1 and K equal to 1. So here also, as you can see, very similarly, memory hold state was 0 to 0 as well as 0, 1. Mixing it up, we are getting 0x. Similarly, in case of 0 to 1, we are getting J equal to 1 and K equal to both 0 and 1, which basically means it is a don't care. Okay. Similarly, you can also try out 1 to 0, which is both toggle or reset. It could be looked at as a toggle or a reset. And this could be looked as a set or a memory hold. 1 to 1, right? 1 to 1 means it could be you are trying to set the circuit, right? Setting the circuit is 1, 0, or you can say toggling, right? Which is 1, 1. Okay. So this is about the excitation table. It is called the excitation table, and you have to sort of use this excitation table in order to design various circuits that we are going to build using the JK flip-flop.